so much. Yes, at first I give you let me say a motivation part of the lecture, that you know a little bit how is the importance, why is metrology, measurement and metrology so important, and what is the history. Then I tell you something about the structure of measurement and instrumentation, because in different countries we understand a little bit different things behind measurement and instrumentation. In Germany, it is one definition. In UK, it is a little bit different. In Russia, it is again a little bit different. And so that you see what contains this field in the different countries. Then we look for the behavior of measurement systems, and we have two kinds of behavior. We have a static behavior and we have a dynamic behavior. The static behavior is the question, what is the output side in reference to the input side when the system is in a static status? No, you have no change on the input side, you have no change on the output side, and therefore what is the dependence from the output side to the input side. And the dynamic behavior is how fast get you the information on the output side. How fast, and especially in industrial measurement and instrumentation, this question is very important when you have an quality assurance task and you have a high production frequency, then have you to check your products very fast, so fast given by the production, and the measurement device has to be at least so fast as the production takt. Therefore, also this is important. And then a big topic, errors. Errors is the main enemy of measurement. Errors is the main enemy of the quality assurance. You have to measure with so less as possible errors, but in many cases, when you have lower errors, you need devices which are more expensive, or you need more time for the measurement, more time and or more expensive. And then is the question, what is enough for the special task? And we have different kinds of errors. We have random errors, we have systematic errors, and especially the systematic errors we can correct. When we know an error, we can correct the error, and that is what we called calibration. The calibration is the correction of systematic errors. And we will look especially how we calibrate a computer-aided device. How can we calibrate a computer-aided device to avoid systematic errors? The most of the measurement devices today contains an microcontroller, a kind of microcontroller that can be very different. It can also be not only a microcontroller, it can also be a PC or what else. But the system, how we calibrate computer-aided the devices, the measurement devices, that is every time the same. And in which language you write it later also, that can be very different. but the systematic is every time the same. And that's what we learn here, how to calibrate an computer-aided measurement device. Sorry. So then we have 2 points, range and precision. I explain the words, and we have a point error propagation. That means when you measure 2 things or 3 things and calculate a result, what is the error of the result? Also, this is important. Let me say you measure a volumina, you have A multiplied with B multiplied with C. ABC has an error. What is the error of the volumina? And that is not only depending from the single errors, that is also depending from the mathematical connection under each other. When you have, for example, a measurement result which is only an additive value, the influence is not so big as when you have it in the powered by status. When you have a measurement result where you say it's powered by this result, the influence is much more bigger. And so the mathematical connection plays also a role. Sorry. And therefore, we look what is the expected value for the result. So then we have a next point, that is the evaluation of series of measurements. That is a little bit statistic. The basic of the statistic, how can we evaluate these measurement results? This is also the connection to, let me say, the quality assurance part, because the measurement and instrumentation deliver the values for the quality assurance. And here we look how can we make a basic evaluation of series of measurements. And then that was, let me say, the most important part of the lecture. That is, I know that is partly, especially the statistics is partly a little bit dry. I try to make it a little bit interesting, but I know it is for many students it is a little bit dry. But this until this point now, it is the most important point of the lecture, because these are the most important points of the lecture, because all what we have done until this point is valid for everything. When you measure a voltage or a speed or a mass, or when you measure the resistance or what else, you can measure what you want. All these points, what we have spoken until this point, is valid for everything, and therefore it is so important. The errors are valid for everything what you measure. The error propagation is valid for everything what you measure. And from this point now, the point or the slide 3, we speak about special measurements. And at first, I have the measurement of mechanical and geometrical quantities. And you see here some things, all with what you can measure, length and angle, then the determination of a position, especially in mechanical engineering. Points you can you use at automated machines, you use possibilities to data mine the position, for example, for a tool with which you work on a project. And I have here make the decision between optical principles and non-optical principles. It's, yeah, let me say, two big areas. And then we speak about the measurement with strain gauges. Strain gauges also very important in mechanical engineering applications. And we measure, we speak also about resulting quantities, because the strain to measure is also a possibility, but mostly we want resulting quantities. For example, when you have balances, you use strain gauges to determine the mass. And how this works and what kind of strain gauges we have, that's that about what we speak. Then we have measurement of forces. Forces are also important to measure, especially the influence on constructions. Then we have acceleration and vibration measurement. That's a huge area, and we make only the absolutely basics, because acceleration and vibration measurement, there exist many books about this, only about this point, but we make only the fundamentals, so that you have the possibility, when you come in contact with this point, that you have the basic and you know which books should I looking for, what are the keywords where I can search in the internet for special purposes. Then we have the measurement of mass, that are the balances. We have two big kind of balances, location independent balances and location dependent balances. And we will speak about the difference and some of the basic principles. Then we have torque measurement. Torque measurement is very important because the multiplication from the torque and the RPM, the rounds per minute, is the power, the mechanical power. And therefore, torque measurement and RPM measurement means I can determine exactly the mechanical power. And when you have an electrical engine, you can say on the input side, the power you can measure very easy, current multiplied with voltage. You have the electrical power. On the output side, you have the torque measurement and the RPM. The multiplication is the mechanical power, and the difference is the efficiency. So that torque is also important. Torque is also important for security purposes, that the machine don't crash when the torque is too high, for example. So then we have measurement of surface quality, of solid materials, surface quality, and determination of the shape, hardness, thickness, values for surface from metal or plastic or what else. Then we have temperature measurement. Temperature measurement in different kinds, and let me say, temperature measurement is also a very, very huge area, because you have extremely much measurement principles in the industry, and we will speak about the basics. We will speak about resistance thermometers. How can I connect the resistance thermometers, and what are the advantages and disadvantages of the different kinds of connection? Here I have one slide, that is only one slide, additional contacting principles, because we decide between contacting principles, where you attach a sensor directly to your measurement object, and we have non-contact principles, where we measure via the temperature ray, so that we can measure also non-contacting. That is more and more important, non-contacting principles. The most important point is that the price of the non-contacting principles is decreased the last 10 years extremely, and you can buy today a non-contacting measurement device for temperature for €50. 20, or let me say 30 years ago, it has had a price 100 times more expensive, €5,000. And this decrease of the price is the reason that we have more and more non-contacting principles. The advantage is that you can measure on rotating machines, where you have a problem to contact a sensor, on rotating machines, or when you have burning processes, when you would like to measure in a burning process on different points the temperature, where it is where you cannot connect a sensor, for example, in waste burning factories, where we burn the waste. You cannot really good contact a thermometer in this waste burning tubes. So then we have an short point, selected principles for measurement of flow level and level limit. Also here exist thousands of principles, and I have made an order to main principles, so that you have an overview about the main principles to measure flow level and level limit. Especially flow is extremely important when you see all the let me say, all the products like gas, like oil, for heating or for cars, or you have a flow measurement. And because on the most of these products you have a high tax, especially in Germany, you have a high tax for gas, for cars, for example. So that the flow measurement is one of the, let me say, finance intensive measurements, where a lot of laws also exist. How and how often have you to calibrate the devices, the measurement devices, for example, at gas stations? Because there is so a lot of money in the game. And level and level limit, it's also, that's only a small point. Then we have measurement of concentrations and analysis measurements. Every time when you would like to measure the concentrations of products in a mix, that can be gas, that can be metal, where you have different kinds of metal in an metal mix, and that can be, let me say, dust in the air, and you would like to say how many particles in which size have we with which concentration in the air. The fine dust problem, you know, it's a huge problem in nearly all industrial countries, the fine dust problem. And we speak about this, the fundamentals: extinction, absorption, emission, and chromatography. That are the basic principles, and I give you an overview about how works this. And then I have some special measurements which plays an important role in the industry. That is humidity measurement, that is oxygen measurement. Then I have a principle infrared spectroscopy that plays a very important role by the determination of the concentration of organic components. Then we have X-ray fluorescence analysis that plays a big role, especially when you have very low concentrations, what you need in many applications in the frame of environmental measurement. When you would like to measure the toxic materials in food or in, let me say, in meat and fish and what else, then it is normally, that are normally very low concentrations, but you have to measure this. Then we have the principle of gas and liquid chromatography. That's an example for this point on top here. And at last one, we have the measurement of dust and soot. This is also our research area in our laboratory. We are working since many, many years in the field of fine dust measurement. We have developed devices for fine dust measurement. At the moment, we have a research project where we try to calibrate these devices with the help of artificial intelligence, with a neural network. And so, of course, in this lecture, I go not so deep in this point, but I speak about short about the fundamentals of the measurement of dust and soot. Then I have a research example, and when we have the time, I must say, when we have the time, I speak about the newest results, what we have in our research in this field, only to give a short overview what we do in our research. So, or let me ask at first, have you questions?
Not any so far.
Okay. When you have questions, you can ask every time. We are not so much. I must have a look. No, I cannot see it at the moment, but we have had, I think, 20 students. That is not so much, so that if you have questions also during the lecture, I let your microphones on. When you have a question, you can by yourself switch your microphone on, can ask, you can make a break for me and ask every time. That is every time the most effective way when we clarify questions immediately and not later. So here we have some sources, but I think the only ones what you need is the script, what I have uploaded, the PDF script, what I have uploaded, because you find in the script all the slides from the lecture. And you can make notes on your slides, and so you can print it out or not. That's all depending from you. Yeah, that would be the introduction, the let me say the overview about the red line in the lecture. And now I have some slides. Yeah, we call it a motivation lecture. That means that we clarify why is this area important? What is depending from the knowledge of this area? And here I have the first slide, the metrology, measurement, and instrumentation. We call it also MME, MMI. The measurability of a quantity is a prerequisite to sell and trade products. When you can something not measure, you cannot sell it. That is very important. For example, the electricity was known, the phenomena was known since hundreds of years. For example, yeah, the people have used it in a circus, so that they have separated the electrons, and so by friction, and let the people touch the contacts, and they got a flash. But that was fun. They have sold the electricity as fun, but not as electricity by itself. And very late, let me say so, 1870, 1880, was clear that you have a current and you have a voltage. And when you multiply this, you have the electricity power. And when you count it over the time, you have the energy. And that's what you can sell. There was an attempt to measure the electricity by the amount of coal what you ship in the steam engine to produce electricity. That was an attempt, because the mass of the coal was the people able to measure. But the dependence from the mass of the coal and the electricity energy was not really good, because the efficiency of the machine was not good, and you have a lot of losses. Therefore, it was not useful. But as it was clear that you can measure the current and the voltage and can multiply this, this was round about 1870, 1880. And since this time, have you an extremely increase of the application of the electricity, because the people was able to sell electricity. And that is a good example that when you not can measure something, you cannot sell it. The next point is the assurance of quality and or enabling of the production. And also here an example. The first microcontroller in the 1970s, 1980s, you have had an efficiency of round about 1 to 2%. That means from 100 microcontroller was working 1 or 2. 98% was rubbish. And it was efficient to produce them, because the alternative would be that you solder all the parts by hand in a huge in a huge box or what else, and that was more inefficient. Therefore, the production has started with an efficiency of 1 or 2%. 98% was rubbish. But over the time, it was clear from what it came. It came from not clean water. It came from particles in the air, and. So that the people have increased the efficiency more and more. And when you see, when you have 98% rubbish and you make it better to 96% rubbish, then have you the double amount of working microcontroller, and that means the half price. And therefore, we have, especially in the field of microelectronics, we have this extremely decrease of the price. That is only a question of the quality assurance. Today, we have 1 or 2% rubbish and not 98%. A calculation was that when we would have the same development as in the electronic industry, when we would have the same in the car industry, a VW Passat would cost today a price of €5. €5 for a car, when we would have the same development like in the electronic industry. Therefore, very, very important quality assurance. So, and then we have also other points. Danger protection, of course. Measurement and instrumentation is important for, let me say, X-ray detection, ray detection in generally, and the warning of the people and so on. And the last point is the acquisition and providing information for operating equipment. What is behind this? This is the automation technology. You can only automate a process when you know about the process, when you know about the measurement values behind this process, then can you control. That means the metrology, measurement and instrumentation is the information grabbing for automation processes. So, and now I show some slides how the development in the history was. One of the oldest points was that the English king said 1 yard, it's a length measurement, 1 yard is the distance between my own thumb and the top of my nose by stretched arm. That means he was the standard. He has defined himself as a standard. The need was that England was a producer of clothes, a lot of clothes, especially wool clothes, and the pressure was that they have an unit to sell these clothes, and so he has defined themselves to a standard. But of course, the disadvantage is the limited living time of the standard, and it's also not really so precision. But today we can say one of this old yard is today 1 meter. That is not very far from each other. That means what we want is more precision. We want not change the value. We want only more precision. And therefore, many examples was set up. In Germany, for example, a mathematician said, we take the people when they come out of the church in the morning and on the Sunday, and we look how we take 16 people, and we take the feet behind each other. You see here all the feet, and say this is one rod, and the mean of the feet is 1 feet. That was the measure. And the precision was better as the precision of the English version to this time. And then a very huge step in the precision was made by a France guy. He has set up a new standard for 1 meter, and he has cast it in platinum. The name was 14. I excuse my French is not good for the French students. You can express this, the name. I'm sure you can express the name better as I. But he has cast this standard from platinum, and that was placed in the Vrai near Paris. And you have here lines, and on the opposite side you have the same, and the distance from this middle line to the other line, that's exactly 1 meter, with the error 0 by definition. The disadvantage is you have only one. You have only one standard, and when the standard is changing, and we know today that the standard is a little bit changing, the standard is shrinking over the time a little bit. It's very, very small, in the range of nanometer, but around 1900, 1920 was developed the measurement method of interferometry. And the interferometry, what we know today as laser interferometry, in this time they have had not the laser, but you can also realize an interferometer with monochromatic light, and that was possible to produce monochromatic light by a prisma, for example, so that we was able to measure with a higher precision as the standard. And that is a problem. How would you like to calibrate? How can you calibrate a device when your standard has a bigger error as your device. That's impossible. And yes, of course. And the second disadvantage was that you have had to make copies for all the countries, and that was distributed by lottery. Germany got one, and Sweden, and all the industrial countries, but everybody know a copy can never have the same accuracy as the original. Also, this is a disadvantage. And so was defined the meter again new. By the way, the amount 1 meter is round about 1 yard. We want not change the length. We want only make the accuracy better. And so 1983, that's not so long time ago, was defined the meter new. 1 meter is a distance which light crosses a vacuum during a time of this seconds. That is a definition. There is no decimal more or less. It's a definition. And the basic is that we say the light speed is a natural constant. And when the light speed is a natural constant, then can we also, via the time, define the distance. But the time has also been defined. 1 second is the oscillating period in resonance of an atom 133 cesium multiplied by this number. The time was earlier defined by a natural constant, and today we have defined all basic values by natural constants, because every country who is able to set up this experiment equipment can produce an own standard. The last one was the kilogram. That is, I cannot say exactly, 2 or 3 years ago, was defined as the last one, the kilogram, by a new natural standard. Yes, the time is an additional problem, because primarily the second was derived from astronomical cycles. That means we know when the Earth is turning 1 time around, it's a day. 1 time around the sun is a year, and you can count it down, the year, to the months, to the days, to the hours, to the minutes, to the seconds. And so was it defined. But the problem is that the Earth, the rotating speed of the Earth is not continuously. It is continuously decreasing. It is, the Earth is going slower and slower, but it is also unsteadiness, because when you have other constellations in the sky, then it can be a little bit faster, it can be a little bit slower, and over the time it's decreasing. That is not much. You see here up to 0.01 seconds time difference by the same position. but for technical applications is 1.01 seconds a lot of time. When you have a computer which is running with an takt frequency in the gigahertz range, then you have a lot of impulses in a time of 0.01 second. And therefore was 1967 the second new defined. The second was new defined as the resonance acceleration period of the cesium isotope. And you can measure this resonance frequency, and then was it connected to this number, so that you have then 1 second. Yeah, from the frequency, the resonance frequency multiplied with this number, you have then the second, and that is extremely constant, much more as the Earth around the Sun. And the problem is, we have here the technical definition, and all the international networks, the computer networks, and the tacts of the computer networks are working with the technical definition, because you cannot stop it. Also, you have to connect to a very constant frequency. And the problem is now these 2 times, the technical time from the definition of the cesium isotope, and we call it the Earth time or cultural time. This is going a little bit with a little bit difference over the time. And then was clear that we have from time to time synchronize these 2 times. And it was in the beginning a huge discussion. Should we make it very often, or should we make it every 100 years to make this synchronization? And the compromise was then, when the difference is more than 0.7 seconds between the Earth time and the atomic time, then we give a leap second in this set. That means, in practical, we work with the atomic time, but when the Earth time is 1 second behind, we say it's now 12 o'clock. Normally it is in the change of the year, will it done. It's 12 o'clock. 1 second later, we say again, it's 12 o'clock. That is his leap second, so that you have a synchronization between both times. But with which we work today, that is the atomic time, not anymore the Earth time. So then we come to a next point, the economical importance. Let me say, the measurement and instrumentation field was also every time used, partly also as misuse, to get more tax and to make money for the for the governments and so on. For example, some examples. Historians have have found that in the old Egypt exist two measures for the lengths. They have had a holy meter and a normal meter. And the holy meter was longer and used for the tax of the king. And the normal meter was shorter and was used for normal trade. So that they have had two different definitions of the meter, one for the tax, so that the people have to pay more tax, and one for normal trade. Or from Germany, an old king, Friedrich Wilhelm III, was a Prussian king, and he has had also a money problem. And he has looked, how can I increase the tax? And he has introduced new miles. That means that the distance of 4 old miles was then equal to the distance of 7 new miles. But the tax was paid per mile, so that he has increased the money from 4 old miles to 7 new miles. That was the increasing of the tax. What was also very important, in the past, we have had not the separation from the measurement unit and the measurement target. For example, in a very small Duketum, Baden in Germany, in the south of Germany, you have had 112 different length measures, 92 area of field measures, and so on. And you see here especially, let me say, liquids, 123 measures for liquids. Today, we say you can measure the liquids in meter, in cubic meter, also in liter, but you can calculate the liter in cubic meter. And you have, for all liquids, one measure. That is not in all countries so. When you go to England, they say a barrel is only for oil and gas. But when you speak about a pint, then is it only beer? And so you have still not the separation of the measures and the target of the measurement. But in this case, a very, very progressive role plays Napoleon. Napoleon, the French imperator, has introduced a unified system for all European countries. He was everywhere, and he has introduced a unified system, the system international, what we use until today. That was a very, very progress in measurement and instrumentation, that he has introduced this unified system. So here I have some examples from my collection of measurement devices that are all length measurement devices. This is in English, this is in German. And you see here for closes, a measurement device for closes. You can put here on top one of the end of the close, and then you can go with your thumb in this hole and can measure. And I have made a zoom from here to here. This is a zoom of this. And what you see here sind imprints of the calibration, because all what you use for commercial measurements has to be checked by an institution from time to time that the measurement value is right. And here you see 1915, 17, 19, 21, 23. That means all 2 years has had this seller of the clothes going to an official authority, and they have checked, has he not shorted his device? And when it is okay, he got the imprint. This system have we in all countries until today. When you go shopping also and you buy fruits